Howdy, howdy, we have this problem where we have an elevator and a counterweight, and we want to find out what the heck is the acceleration going to be of that system. Well, first of all, if the elevator moves down, the counterweight's going to move up, and if the elevator moves down 2 inches, the counterweight moves up 2 inches, and so on. So the idea is that these will have the same change in speed, but one will be going up and the other one will be going down with the same acceleration amount, but they have different accelerations because they're going different ways. That's confusing. That's okay. Well, whenever we do something like this is a complicated problem, but whenever we do something, we have to kind of come up with our assumptions. So what is going on in this system here? Well, first of all, we're going to say that G is the gravitational field strength of 10 newtons for every kilogram. To kind of simplify things a little bit. And also, all this system, the pulley system and the ropes and all that, is going to be ideal, which means we don't lose energy to it. We don't have to worry about the mass of anything. Yeah, it takes no effort to move those wheels, etc., etc. That means we just deal strictly with the forces of the elevator and the counterweight, and that's it. The next thing that we're going to do is come up with a system schema, and all we have to do is list all of the objects that are there. And sure enough, we have the elevator, we have the counterweight, the C-dub, counterweight, and then we have the earth field as well, causing all sorts of havoc to the system here. And what's interesting is that each of these objects can be its own thing, but the system, we're going to call the system both of these objects here. That's kind of cool. That means that the only external forces are going to be the weight acting on the elevator and the weight acting on the counterweight. And then you have to think, how are those forces adding together or subtracting? How are they doing that? Well, take the point of view of the elevator and say, hey, which way is the elevator going to go based on our intuition? Well, this has more mass and thereby weighs more than the counterweight. So the system, if we started it from rest, we're going to have the system the counterweight goes up and the elevator goes down. Okay, makes sense. So that must mean that there is going to be a net force downward. So our net force is going to be downward because we expect it to go from rest to faster going down. Okay, cool. That means our acceleration for the elevator is going to be downward. If we think about the system being both the elevator and the counterweight, we can kind of squish them into a tiny little conceptual blob that has no size, and then we can start putting arrows on it and saying, hey, this is our free body diagram. The weight of the elevator, we'll call that FGE, and the weight of the counterweight oppose each other. Look at that. The weight of the counterweight oppose each other. I don't like that color. Let me change that color to something a little more gross. Okay, perfect. And this is going to be the weight of the counterweight acting in the opposite direction of the other weight. And yes, we know that the weight isn't going upwards anywhere. The weight is pulling down on the counterweight, and because of the ropes, we're getting this pull up on the elevator. So this is kind of like from the point of view of the elevator, we're seeing an upward pull by the weight of the counterweight and a downward pull by the weight of the elevator. It's that simple, really, when it comes down to it. So how do I figure out weight? Oh yeah, weight is just mass times the gravitational field constant. And since we are using the simplified version, it's pretty straightforward. I just need to move the decimal over 1. So the weight of the counterweight is just going to be 8,500 newtons. And the weight of the elevator is going to be 10,000 newtons. Cool beans. So the net force is going to be the subtraction of those two, and it's just going to be 1,500 newtons. So the acceleration is going to be based on that. So now we get to figure out what the acceleration is. We know that the mass of both of those things work together. They're both part of the same system. So we have the mass of 1,850 kilograms. All right, so we'll look at that and give that a different color, like, oh, orange. Sure. The mass of the whole system together is 1,850 kilograms. The net force is 1,500 newtons. And so if we want to find out what the heck our acceleration is going to be the net force divided by the mass of the system. That's going to be the 1,500 newtons, right? We have that 1,500 newtons. We're going to paste it right over there, blah, and then we're going to divide it by the 1,850 kilograms. Wow. Divide those two together, we get some crazy number, and our acceleration ends up being rounded to 1 decimal, ends up being 0.8 meters per second squared. A Newton divided by kilogram comes out to acceleration units, so I just know to change that to meters per second squared. And that's it. That means the elevator is going to accelerate downward at 0.8 meters per second squared. The counterweight is going to accelerate upwards at 0.8 meters per second squared. Cool beans. Thank you.